All right, so we've been looking at this stuff on linear equations in one variable, and it can be kind of tough to like get through all of it. So today we're going to try to make it as easy as possible for you. Basically, we're going to extract the core ideas, the most practical part, so you can understand this really, really fundamental concept
Yeah.
without it feeling like, you're back in school slogging through like a huge textbook. So we've got these excerpts here that really lay out, exactly what these equations are. And what we want to show you is why these things aren't just, some abstract exercises that you do in a math class, but they actually pop up in some surprisingly useful places.
Yeah, exactly. I think that's kind of our goal here is to go beyond, just the what's and really get into the why and the how of these equations. Linear equations in one variable, it can sound a little dry, a little bit technical, but it's a fundamental tool,
Yeah.
in algebra. And understanding them can unlock a lot of problem-solving power.
Okay, so let's start with the basics. I mean, what exactly are we talking about when we say, algebraic equation? Like the material you sent even makes a point of defining this right at the beginning. What does it mean?
Yeah, it really does. I mean, at its very core, it's a statement of equality. It's saying that one thing is the same as another. And what makes it, algebraic is that it involves variables which we use letters to represent. And those letters represent unknown numbers. But those variables and numbers are connected by an equal sign. And that equal sign is very important. That's what makes it an equation
Hmm.
and not just a bunch of, numbers and symbols and letters.
Right,
So you can almost think of it like a balanced scale.
right.
Whatever's on one side has to weigh the same as what's on the other side.
Right, so if we just see something like 5x plus 2, that's an expression, but as soon as we write 5x plus 2 equals 12, that's when it becomes an equation. And with that equal sign, now we have the idea of two sides.
Exactly. You have the left-hand side, or LHS, and the right-hand side, or RHS. And in that example, 5x plus 2 equals 12. 5x plus 2 is the LHS, and 12 is the RHS. And getting comfortable with that structure, the left and the right, is really the very first step, in understanding and solving equations.
Okay, now we are diving specifically into, these linear equations in one variable. So let's break down that phrase a little bit because it does sound a bit technical. What does one variable actually tell us?
Well, it's pretty straightforward. It just means that in the entire equation, you're only going to find one single letter that's representing that unknown value. So you might see an X or a Y or a Z, but you're not going to see an X and a Y in the same equation if it's a linear equation in one variable.
Yeah.
It's all about solving for that one, single mystery value.
Okay, so just one unknown that we're trying to uncover. Now, the word linear also seems really important here. What makes an equation linear? And then the source material really emphasizes this distinction.
Yeah, it does. And the key to the linear part is the highest power that that single variable is raised to. So in a linear equation, that highest exponent is 1. You can think of the variable as just standing on its own. It's not being squared, it's not being cubed, nothing like that.
Right, so the material even gives some pretty good examples to illustrate this point. Things like 2x plus 1, 3y7, those are all linear.
Hmm.
But then it contrasts these examples with things like x plus 1 or u plus y, or even longer ones like 1 plus z plus z plus z. And it points out that these are nonlinear. So what makes them different?
Well, like the source points out, the variable in those cases being raised to a power that's greater than 1,
Mhm.
you see at the top there in x and y, those are a really good indicator that this isn't a linear relationship anymore.
Mhm.
And the higher powers of z in that longer expression are doing the same thing. Linear equations, when you graph them, they form straight lines. That's where the name comes from. Nonlinear equations will create curves.
Okay, that makes a lot of sense. I never actually thought about the fact that linear relates to a straight line, but it definitely makes sense. So we've got an equation. It's got one variable. That variable isn't being raised to any power higher than 1. That's our linear equation in one variable. But what are we actually trying to do with this thing? What's the ultimate goal when we see one of these?
The goal is to find the solution. That's what we call it. And the source material defines it really nicely. Basically, it's the specific value or values, but in linear equations, in one variable, it's usually just one. It's the specific value that you can substitute for that variable that will make the left-hand side perfectly equal to the right-hand side. It's like finding the exact weight that you need to put on one side of our scale to balance it out.
Right. Okay. And the source gives this really helpful example, 2 by 3 equals 7. So how do we check if a particular number is actually the solution to that equation?
You just take that number and plug it in wherever you see the variable. So you substitute it in, and then you work out both sides of the equation. You calculate them independently, and you see what you get. If the results are identical on both sides, then you know that number is a solution. So the source shows that if you try x, please 5 in that equation, so it becomes 2 times 5 minus 3. Well, 2 times 5 is 10, minus 3 is 7. And the right-hand side is also 7, so that means x equals 5 is a solution. But if you try something like x equals 10, then it becomes 2 times 10 minus 3, which is 20 minus 3 is 17. And 17 is not equal to 7, so x please 10 is not a solution.
So it's all about finding that magic number that makes the two sides balance out. So how do we actually find the solution? The source talks about this balancing act. What is that?
Yeah, the fundamental principle for solving any equation is that you have to maintain the equality. You got to keep the left-hand side and the right-hand side balanced. Think back to our scale analogy. If you do something to one side, you absolutely have to do the exact same thing to the other side if you want to keep it level. And that goes for any mathematical operation, whether you're adding, subtracting, multiplying, or dividing. You have to apply it equally to both sides.
That makes a lot of sense. It's like we're trying to get that variable alone on one side of the equation by undoing everything that's being done to it, but we have to do it, in a fair way on both sides.
Yeah, you got it.
Can you maybe give us an example, like a simple equation, and show us how this works in practice?
Absolutely. Let's take the equation 2 by 3 equals 9. So our goal here is to get x all by itself on one side. So right now, x is being multiplied by 2, and then we're subtracting 3. So to isolate x, we need to kind of reverse those operations, starting with the subtraction. So to get rid of that 9 days 3 on the left-hand side, we can add 3. But remember, we have to do the same thing to the right-hand side. So our equation becomes 2 by 3 plus 3 plus 3 equals 9 plus 3, which simplifies to 2x equals 12. Now, x is being multiplied by 2, and the inverse of multiplication is division. So we're going to divide both sides by 2. So 2 by 2 equals 122, and that gives us x is 6. And if you want to double check and make sure you got it right, plug 6 back into the original equation. 2 times 6 minus 3. 2 times 6 is 12, minus 3 is 9. And 9 is what we had on the right-hand side, so that confirms that our solution is correct.
Okay. I think that step-by-step walkthrough is super helpful because it really shows that balancing act in action. Now, the source moves on to a slightly more complex situation, which is equations where the variable, that unknown letter, is actually on both sides of the equation. And this looks a little trickier.
Yeah, it can look a little more involved, but that core principle of maintaining balance, that's always going to be our guiding star. And so the key here is just to think strategically about how we can manipulate the equation, always performing the same operation on both sides, so that we can get all of the terms containing the variable all together on one side of the equal sign, and all of the constant terms, which are the numbers by themselves, all together on the other side.
Right. Okay. And so the source uses this example, 2 by 3 equals x plus 2. So can you walk us through how we would tackle this one, following those steps they outline?
Sure. So our first aim is to get all of those x terms together. So if we look at the equation 2 by 3 equals x plus 2, we have an x on the right-hand side. So to bring it over to the left, we can subtract x from both sides of the equation. So we have 2 by 3 x plus 2x, and that simplifies 2 by 3 equals 2. So you see, by subtracting x from both sides, we essentially move that x term from the right-hand side to the left-hand side, and we also changed its sign in the process. And that's often called transposing a term, meaning you move it to the other side of the equation and you flip the sign. Now all we have to do is get x by itself on the left-hand side. So we have x minus 3. So to undo that subtraction, we add 3 to both sides. By 3 plus 3 equals 2 plus 3, which gives us the solution, x equals 5.
And the source actually also deals with some equations that involve fractions. I have to admit, just the sight of fractions makes me a little uneasy. What's the strategy for dealing with those?
Yeah, they can look a little intimidating, but there's actually a really nice technique that you can use to just make those fractions disappear. The source gives this example. 5 by 2 plus 72 will equal 3 by 14. What's the trick here?
Well, the key is to look at all the denominators in the equation, so the bottom numbers of the fractions. So here we have 2 and 14, and find what's called the least common multiple, or LCM. It's the smallest number that all of those denominators will divide into evenly. So for 2 and 14, the LCM is 14. And then you multiply every single term in the equation on both sides by that LCM. It's like finding a common currency so you can get rid of all the different denominations.
Exactly. So if we multiply every term in 5 by 2 plus 72 equals 3 by 14, let's see what happens. So when we multiply 14 by 5 by 2, the 14 and the 2 cancel out, leaving us with 7 times 5x, which is 35x. And next we multiply 14 by 72, and again 14 divided by 2 is 7, so we get 7 times 7, which is 49. And then on the right-hand side, when we multiply 14 by next 3 by 14, the 14's cancel out completely, and we're left with just negative 3x. So our original equation with all those fractions is transformed into 35x plus 49, which looks a lot more manageable. And now we can just solve it like we were doing before. We can get all the x terms on one side and the constants on the other. So if we add 3x to both sides, we get 38x plus 49 equals 0. Then we subtract 49 from both sides, so we get 38x equals 49. And finally, to get x all by itself, we divide both sides by 38, and we end up with x equals 4938.
Okay, so you don't even have to like work directly with those fractions, you just get rid of them right away.
Yeah,
Yeah.
exactly. And the source also, walks us through a couple of examples that get a bit more involved, because now we have to do some simplifying before we can really start isolating the variable. Like we have to open up brackets, or sometimes they're called parentheses, and we have to combine terms that are alike. So let's look at one example. Example 16, which is x plus 1, 3 plus x plus 6 pi plus 3, 6.
All right.
So just like with the fraction problem we just did, the first thing we want to do is get rid of those denominators. So we have a 3 and we have a 6. The LCM of 3 and 6 is 6, so we're going to multiply every single term in that whole equation by 6. So we multiply 6 by x plus 1, 3. The 6 and the 3 sort of cancel out, leaving us with 2 times x plus 1. And then when we multiply 6 by x plus 6, 6, the 6's cancel out completely, and we're left with x plus 6. And then same thing on the right-hand side, when we multiply 6 by x plus 3, again, the 6's cancel out, and we're left with my 3. So our equation now looks like this: 2x plus 1 plus x plus 6 by 3.
Okay, so now we have to deal with all those brackets.
Right. We're going to open them up, as the source says, using what's called the distributive property. So we multiply the term that's outside the brackets by each term that's inside the brackets. So, for example, we have 2 times x, which is 2x, and then we have 2 times 1, which is 2. So 2x plus 1 becomes 2x plus 2. And then the other terms, they just stay as they are for now. So now the whole equation is 2x plus 2 plus x plus 6 by 3. And then the next step is to simplify each side by combining what we call like terms. So terms that have the same variable raised to the same power. On the left-hand side, we have 2x and x, so those can be combined into 3x. And then we have 2 and 6, which we can combine to 8. So the left-hand side becomes 3x plus 8, and the right-hand side is already pretty simple, as by 3. So the equation is 3x plus 8 equals by 3. So now we can start solving for x. So let's subtract x from both sides to get all the x terms together. 3x plus 8x was by 3x, which simplifies to 2x plus 8 equals 3. Now we just want to isolate the x term, so let's subtract 8 from both sides. 2x plus 8 equals minus 3 returned, which leaves us with 2x plus minus 11. And finally, to solve for x, we divide both sides by 2. 2 by 2 equals go 9 equals 112, which means x1 equals 112.
Wow, so we even had to deal with negative numbers in there. Okay, and there's one more example in the source that's along these lines. It's example 17, 5 by 2, 2 by 7 equals 2, 3 by 12 plus 72. I mean, this one definitely looks like it has even more steps involved.
It does look a little intimidating, but we're going to use that same step-by-step approach that we've been using. So first things first, let's expand those brackets. So on the left-hand side, we have negative 2 multiplied by 2x, which gives us negative 4x, and then negative 2 multiplied by negative 7, which gives us data plus 14. So the left-hand side now looks like 5 by 4x plus 14, and we can combine the x terms and get x plus 14. Now on the right-hand side, we have 2 multiplied by 3x, which is 6x, and 2 multiplied by negative 12, which is negative 1. So now the right-hand side looks like 6 by 1 plus 72. Now we can simplify the constants on the right-hand side. We have negative 1 plus 72. And to make it a little easier to add those together, it's helpful to have a common denominator. So let's write negative 1 as negative 22. So negative 22 plus 72 equals 52. So now our whole equation looks like this. X plus 14 equals 6x plus 52.
Okay, great. We did all that simplifying.
Right.
So what's the next move?
Now we want to get all the x terms on one side and all the constant terms on the other. So let's subtract x from both sides. X plus 14, x plus 52x, which simplifies to 14 equals 5x plus 52. Next, we want to isolate that term with x in it. So let's subtract 52 from both sides. 14, 52 equals 5x plus 52, 52. So that gives us 14, 52 equals 5x. Now to do that subtraction on the left-hand side, we need to rewrite 14 with a denominator of 2. So 14 is the same as 282, right? So we have 282, 52 equals 5x, which is 232 equals 5x. And finally, to solve for x, we just need to get rid of that 5 that's multiplying the x. So we do that by dividing both sides by 5, which is the same as multiplying by 15. So x equals 232 times 15, which means x equals 2310.
So even when we have fractions and brackets in there, that same basic strategy that we've been talking about, that we've been practicing, it still works. We just do the simplifying first, and then we use our balancing operations to isolate the variable and find the solution.
Exactly, yeah. And the source actually has this nice little section called What Have We Discussed?, which kind of summarizes everything we've been talking about. It points out that we've been looking at these equalities involving a single variable raised to the power of 1, and these can appear on either side of the equation or both sides of the equation.
Yeah. And it's worth reminding everyone, that fundamental rule that we keep coming back to. Whatever you do to one side of the equation, you absolutely have to do to the other to maintain that balance. And that often involves transposing those terms from one side to the other to get the variable terms on one side and the constant terms on the other.
Exactly. And before you even start trying to isolate that variable, it can save you a lot of trouble down the road if you just take the time to simplify both sides of the equation first. So that means opening up any brackets, combining any terms, and dealing with any fractions, often by multiplying by that LCM like we were talking about.
So hopefully by now you're starting to get a really clear picture of what linear equations in one variable are and what those fundamental tools are that you can use to solve them. And these aren't just, abstract mathematical puzzles. The source material even touches upon the fact that these have real-world relevance.
Yeah, definitely. I mean, even that "what have we discussed" section hints at the fact that these things are really useful for problem solving. Like, linear equations are kind of the backbone of solving all sorts of practical problems, like figuring out relationships between numbers, ages, calculating perimeters, even dealing with different denominations of money. They give you a way to take an everyday scenario and translate it into math language that you can then solve in a really systematic way.
Which brings us to our final thought for you. Think about this idea, this fundamental idea of maintaining balance. This is at the heart of solving all of these algebraic equations, but it's not just a mathematical trick. It's something that we see in all different areas of life, like physical systems, how they try to find stability, or relationships, how they need that give and take. Even economic models, how they try to balance supply and demand. What other systems or situations can you think of that really rely on this idea of maintaining equality? It's pretty core how a simple concept in algebra can give us a framework for understanding a whole bunch of different phenomena.
Yeah, absolutely. And we hope that this deep dive has given you a really solid foundation in understanding and solving these linear equations in one variable. And we hope you'll keep exploring these ideas and join us for more deep dives as we unpack all sorts of other intriguing mathematical concepts.